This captures what knowledge and graph technology really represents. It is a formal specification of a shared conceptualization. And that's what we want to give to our agents. We want to give them our conceptualization of the universe, our domains, okay? And now what's happening is you're getting the convergence of something that is probabilistic, the agents, the LLMs, with the more formal representations that you have with ontologies. And so this term is now being used, you're hearing this a lot, neurosymbolic AI. Sounds pretty fancy, but it's really neural networks tied into symbolic AI, which rule-based systems come under that category, as do the knowledge graphs that we're assembling. And so what I like to argue is that neurosymbolic AI sort of represents a way to keep the LLM on its guardrails, because LLMs are by nature probabilistic. People worry about hallucinations, but that's the feature. That's actually a feature of large language models. It's who we are. We hallucinate in a way. We imagine things that may not exist, and then we turn them into reality. And that's what large language models do in a way, okay? So let's just quickly overview what ontologies are. They're not complicated. They're basically our representation of entities and their relationships to other entities. And these entities have properties. And this whole concept of graph databases arose when people began to realize that relational databases, sticking data into tables, was too restrictive. You wanted to add something new to a relational database, so you had to add a new column. Man, then you have to redo the whole structure. With a graph database, you can just attach another item. You can just attach a property. You can attach a relationship, okay? So the question often arises, okay, I get it. I need to have an ontology to represent in a formal way what my organization is doing. How do I do it? Okay? There are a couple of ways you can approach it. You can have a top-down approach or a bottom-up approach. Top-down approach is you get the experts together and they sit down and analyze the domain, come up with the entities. What do we have? We have purchase orders, we have customers, we have customer representatives, and we're going to structure them. They have properties. These are the relationships. Okay, that's one way. And this models what we were doing back in the 80s when I was involved in expert systems. Everybody thought expert systems was the way to do AI. Symbolic AI was the way to go. Companies rose, millions of dollars were spent. The Japanese created this future world project in the late 80s. People in America, my son was taking Japanese in school because of these expert systems, but they couldn't scale. They couldn't scale, and then we went into a kind of AI winter. Where did neural networks come from? Neural networks were put out there in the 60s, but they couldn't scale because we didn't happen to have NVIDIA, who was off making GPUs to make reality of the video games fantastic. And then someone said, let's turn these things over to the neural networks, and of course, that's kind of why we're here now. So the other way you can, that people are adding to or creating ontologies is from the bottom up. For example, customer reactions. What are the things the customers are involved in? Hey, these entities, these relationships, let's add this to our ontology. Let's add this information to the graph. Now, as a help, it's helpful to be aware that there are existing taxonomies that people have been working on for the last 15 to 20 years. Things like schema.org, which has a whole set of terms and relationships, so you don't have to reinvent the wheel. In fact, it's to your advantage to use some of these ontologies. FOF, a friend of a friend, for modeling social networks. The Dublin Core, which was an early attempt to come up with terms for describing research papers and books and so forth. So there's a whole series of things. In fact, Wikipedia is based on an ontology called DBpedia. So when you do a search on Wikipedia, it's looking things up in its giant graph database. So this stuff has been out there underlying a lot of what we already do. So take advantage of these things that already exist. Okay, now, what do you do when you build your ontology? Okay, so what? I know what these entities are. I know what their relationships are. They have properties. How can I do anything with them? Well, there are other augmenting technologies, auxiliary technologies. Things that we call things like RDFS, which is a technology, and OWL, which I'll talk more about. So these kind of sit over to the side of your graph. So I'm not going to talk about, ontology is a big word and it's often confusing and used in many ways. But think you have a graph data structure, okay? And you have the entities and relationships, but you want to apply some control over them. Or you want to be able to make inference over them. So, for example, there is some terms in this technology called RDFS, domain and range. So if I say teaches has a domain of teacher, that means if I say Bob teaches Scooter in my text, I can infer that Bob is a teacher. And if I say all teachers are persons, then this statement lets me know if I say Bob teaches Scooter, now I know Bob is a person, Bob is a teacher. What about Scooter? If I say teaches has a range of student, that means the right side of the verb, then Scooter is a student. And now I have this extra information into my system. OWL also has a series of properties that allow you to make some inferences. So a transitive property. Transitive property says if Sue is an ancestor, like ancestor is a transitive property. If Sue is an ancestor of Mary and Mary is an ancestor of Anne, then Sue is an ancestor of Anne. Okay, this was not initially into my graph system, but with applying these functional properties, I can then add and augment the system with this extra data. So that's very useful. Then there's some properties called functional properties, which means only one. So has father is a functional property. You can only have one father. You can only have one mother. That is a functional property. Okay? So that can serve as a constraint